limits that result in indeterminate forms. Alright, so you guys know indeterminate forms to be those forms that when you try direct substitution into a limit, you might get something like 0 over 0 or infinity over infinity. There are others, of course, but those are the two big ones and kind of the two that we care about today. They're called indeterminate forms because they tell you absolutely nothing about what the limit actually is. It doesn't tell you whether the limit exists. It doesn't tell you that it doesn't exist. And it certainly doesn't tell you anything about what the limit actually equals. If you get 0 over 0 or infinity over infinity out of direct substitution into a limit, the real limit could be anything. It could be a negative number, it could be a positive number, it could be 0. The real limit could also be infinity. But there's no way to know any of that from getting the indeterminate form. So what you often have to do, or what you have had to do in the past when you get an indeterminate form, is some form or other of algebraic manipulation. So if we just look at these two limits right here, and I'm just going to do these real quick because it's not important that you guys remember how to do this, because what we're learning today is going to allow you to avoid doing this. But what you would do is, previous to this, in Calculus 1, in evaluating these limits, first note that direct substitution produces an indeterminate form. Because if you try to plug in -1 into this, because x is going to -1, if you try to plug in -1 into this, you get 0 over 0. Which is an indeterminate form, which means that that there is some sort of algebraic manipulation that's probably possible. If instead you took this and you factored the top, well, that'd be 2 times x squared minus 1. Like if you factored a 2 out, and even more than that, let's take this x squared minus 1 and factor it into x plus 1 and x minus 1. So that's how the entire top factors. And of course there's a limit statement. X is going to -1. So this so you sort of see that this factor, shows up in the top and the bottom, and that you can cancel it out because it's on the top and bottom of a fraction. But it's actually this factor that appears that sort of causes this to equal 0 over 0, because it's x. It's the factor x plus 1. If you plug in -1 into that, it's going to multiply the top and bottom by 0. So if we get rid of it, what we'll have is the limit as x goes to -1 of just 2 times x minus 1, which if you do direct substitution on that, -1 minus 1 is -2, times 2 is -4. So the limit is -4. The real limit is -4. For the second one, if we try direct substitution, putting aside the fact that infinity is not a number and that we can't actually can't manipulate an infinity like we can with numbers, if you just sort of ignore a bunch of mathematical rules and do it anyways, what you get is 3 times infinity squared minus 1 on top, and 2 times infinity squared plus 1 on the bottom. Just make sure that you know that you cannot actually do this, but this is basically what happens. And so you get infinity over infinity. Because, you know, square infinity, that's infinity. Subtract 1 doesn't matter. Same thing here. So that's an indeterminate form. Right, so what you can do instead is you can take this and what you can do with this is you can look at that x squared that's in the denominator and say, okay, I'm going to take every term on the top and the bottom and divide it by that degree of x. So there's an x squared in the denominator, so divide every term by x squared. Okay, what happens then is that this becomes 3 minus 1 over x squared over 2 plus 1 over x squared. And this is the limit as x goes to infinity. Okay, so the 3 and the 2 are just going to be a 3 and a 2. And these terms in the back, if the bottom is going to grow to infinity, these terms themselves are going to shrink to 0. Like if you divide by a really big number, the result is really, really small. If you imagine 1 divided by 10 billion, million, trillion, that's going to be, it's going to be vanishingly small. So this becomes 3 halves, which you don't even have to substitute anything into that to get that it's 3 halves. So the limit there is 3 halves. So you get an indeterminate form like that. The real limit can be anything. Okay, but what we are learning today is sort of a way to avoid the need to do any of this stuff. All right, so we're not actually going to be doing any of this. This is what we're trying to avoid having to do. Okay. All right, you can do this. Sometimes you can do the same with transcendental functions. Again, don't worry too much about this method, but if you look at this, a way that you could rewrite this, and I'm not even going to go through the trouble of like writing it over again. The way that you could write this is if you have e to the 2x, right? That's e to the power of 2 times x. Another way to write that is e to the x squared. Because if you have a power to a power, you multiply the powers together. That also works in reverse. If you have 2 things being multiplied together in a power, you can sort of decompose them as these sort of stacked powers. Oh, right. And this is the limit as x goes to 0, of course. And then this on the top here becomes a difference of 2 squares because the first term is e to the x squared and the second term is 1 squared. So you can decompose this further as a difference of 2 squares. So one of the factors will be e to the x plus 1 and the other will be e to the x minus 1. All over the same e to the x minus 1 that was there before. And you just sort of, cancel. Then you try plugging in 0. E to the 0 is 1. 1 plus 1 is 2. Right, so you can do some of these same algebraic tricks on a limit, even if the limit itself is not algebraic in nature. And technically this just counts as a transcendental function because it's got that exponential in there. Okay. So this sort of thing, can happen too. But there are situations. Oh, right. And the first thing we should have checked is that direct substitution gives an indeterminate form, which it does. That'll be e to the 2 times 0 minus 1 over e to the 0 minus 1. That's going to equal 0 over 0. Because anything to the 0 power is 1. So we do get an indeterminate form, which means that there is some sort of, that's sort of what we should check first. Okay. So sometimes that's possible to do with transcendental functions inside of limits as well. But sometimes you can get indeterminate forms and there is no recourse. For example, if you have a limit like this, it does, if you do direct substitution on this, you will get 0 over 0. But there's nothing to do, there's no way to manipulate this algebraically to make it into something that you can, there's no way to cancel anything out. That exponential on the top and that x, that algebraic x that's on the bottom, there's not really anything that they sort of have in common, or there's no real way that they interact with one another in any clever way. So sometimes you can get an indeterminate form, and there won't be a way to sort of do any sort of clever algebraic manipulation and be able to evaluate it. And so we need a way to find the actual limit, because it definitely, the limit, of course, is not whatever 0 over 0 is supposed to be. The limit's probably some kind of number or something. Possibly. So if we were to graph this and check the limit graphically, here's the graph of that function that's at the that we're trying to take the limit of. We're trying to take the limit as x goes to 0. So if you look at where x is 0 and you look at the value of this expression, while you can't plug in 0 exactly, like you can't actually plug in 0, you can sort of see what's happening around it, before and after, and it pretty much appears to, from both sides, be approaching a value of 2. So the limit is probably 2. And if you do the same thing with a table, that will sort of corroborate that. If you get closer to 0 from the negative side, you sort of see that these values of this expression are quickly approaching what appears to be 2. And the same thing as you approach 0 from the positive side. If you start at 1 and then sort of work your way down to 0, your values are going to get closer and closer to 2. So your limit is probably 2. But it would be nice to have a sort of mathematical way of confirming that this is true, other than just sort of, oh, it looks like it on the table, or it looks like it on the graph. So this is probably not the definition that you want to be writing down, but if you have a quotient of a limit, that is, you're taking a limit of some sort of quotient, something's on the top and something's on the bottom, and you're getting an indeterminate form, you can get the actual limit by just taking the derivative of the top and then taking the derivative of the bottom. So here's the actual statement of, no, this is not it. Don't worry too much about this. No. Saying, yeah, don't worry about that. Okay. So this is probably the best statement of L'Hopital's rule. If you're taking a limit of a quotient, you can just sort of ignore the as x approaches c. I mean, it's true, but it's not really, that's not really something, the part that you're going to want to be remembering. So if the limit produces the indeterminate form 0 over 0, what you can do is, to avoid getting 0 over 0, just take the derivative of the top of your limit and take the derivative of the bottom of your limit and use those instead. You can also use it for when you get infinity over infinity, or any of these sort of other signed variations of infinity over infinity.
0 over 0, we use a sub rule on substitution. Just
Wait, what?
When you say like 0 over 0, we use a substitution. Or after the...
Yeah. So like if you try to directly substitute and you get one of these indeterminate forms, you're not gonna, like, that's the only way you're gonna be getting these indeterminate forms, is if you try to plug in the actual value of the actual value of the sort of the target number, the c. But yeah, if you directly substitute and you get one of these indeterminate forms, you can use this sort of I mean, I wouldn't want to call it a trick, but it's a useful way to get around having to really do anything except take two derivatives. There's no, you don't have to cancel anything out. You don't have to, do anything weird. And while knowing this may have made certain limits in Calculus 1 a lot easier, you can probably see why you didn't learn this in Calc 1. So, if you directly substitute and you get one of those indeterminate forms with a 0 over 0 or infinity over infinity, you can use L'Hopital's rule to find the limit instead. Okay. So, right now, I'm just going to write down a couple of indeterminate forms that you might see. Okay. You might see 0 over 0. You might see any number of variations on infinity over infinity. And these are the ones that you want to be, looking for if you want to use L'Hopital's rule. There are others. For example, infinity minus infinity. Or negative infinity plus infinity, basically the same thing. 1 to the power of infinity, let's say infinity to the power of 0. 0 to the power of 0. but not 0 to the power of infinity. That's probably all the good ones. Okay. And so it is possible to get these other indeterminate forms, but you want to eventually get them to be this or this, so that you can use L'Hopital's rule. So you might start off with some other indeterminate form, that you have here, but you're going to want to make them into these. Now, what is not an indeterminate form and therefore, you can't use L'Hopital's rule on these. These are not indeterminate. Or in other words, they are determinate. 0 over infinity, that's just 0. Well, we'll say that just tends towards 0. Infinity divided by 0, well, that just tends towards infinity. Infinity plus infinity, those are just going both in the sort of positive direction infinitely, so if you just add them together, you end up with infinity again. Same with if you have negative infinity minus infinity. It's going to just end up being a further negative infinity. Oh yeah, I forgot about one. 0 times infinity over here on, is also indeterminate, and it's another one that you're going to want to get to be like these. Okay, what else is not indeterminate? 0 to the infinity power, that's just 0. Okay, so these are not indeterminate, and if you have one of these over here, you can't use L'Hopital's rule. But you won't have to, because since they're determinate, those are what those limits will be. So just wanted to get that sort of, what is indeterminate and what is not indeterminate sort of out of the way before we actually start using L'Hopital's rule. So you can also use L'Hopital's rule for one-sided limits. That's not really an exception. Well, it's not an exception, but it's not really notable enough to sort of be its own separate thing. But if you wanted, there you go. It just has like a little plus sign on the C to indicate that you're approaching from the positive side. You could also do it with a little minus sign on the C if you wanted to be approaching from the negative side. But basically, it behaves the same way for one-sided limits, which is nice, but not super notable. All right, so we're going to evaluate this limit that we could not evaluate through any sort of algebraic method. But remember that the limit from the graph and from the table appeared to be 2. It appeared to be the value 2. Okay, so first you must, before you try to use L'Hopital's rule, you gotta verify that you do get an indeterminate form, 0 over 0 or infinity over infinity. So just over here, through direct substitution, e to the 2 times 0 minus 1 on top, and just a plain old 0 on the bottom. That does result in a 0 over 0, which, it's not... I mean, it'd be great if that were an actual number, but if we're going to get an indeterminate form, at least it's that one, as opposed to a weirder one. So this is what we want if we're wanting to use L'Hopital's rule. Okay. So what you do instead is you take this, and it should equal the limit as x approaches 0 of the derivative of the top over the derivative of the bottom. And of course you don't have to write this little extra step. But this is just sort of, this is what's happening. So that's the limit as x goes to 0 of... Now the derivative of an exponential is just itself, possibly multiplied by some constants after. But so the derivative of e to the 2x is going to be e to the 2x times 2 because of the chain rule. It's a composite function. The inside function is 2x, and so you got to multiply by the derivative of that 2x at the end there. And the derivative of minus 1 is nothing, so that doesn't even appear. And so, if you want to, you can say it's 2e to the 2x. Okay, and the derivative of the bottom here, the derivative of x is just 1. So, okay, so you have applied L'Hopital's rule once. Get this. So if you try direct substitution now, that'll be basically 2e to the 2 times 0 over 1. So that's 2. Which, sort of jives with the graph and with the table. And, okay, so at this moment, what's going on here? Okay, there's 2. Oh, right, this approaches infinity. Okay. So as a matter of fact, if we go back to the ones from the beginning that sort of, allowed for that, some level of algebraic manipulation, we can actually use L'Hopital's rule on that as well, on those rather. Okay. So these both produce the indeterminate forms that, L'Hopital's rule requires. You go ahead and use L'Hopital's rule on this, you'll get the limit as x approaches -1 of the derivative of the top is 4x, derivative of the top is 4x, and the derivative of the bottom is 1. And if you plug -1 into there now, you'll get that same -4 from here. Go ahead and do that with this. Take the derivative of the top. That's 3x. Okay. Take the derivative of the top. The derivative of 3x squared is 6x. Minus 1. Differentiates into nothing. And the bottom becomes if you take the derivative of the bottom, that's 4x, which you can sort of cancel out those x's. And 6/4 is just 3/2. That same 3/2, that's from here. So, knowing this, you will never have to algebraically manipulate a limit again. So here's where we were. Right. So the limit of this this one that was not, algebraically manipulable is 2. This might seem like it's saying the same thing, but it's got a small difference, not one that really matters. It's just saying that you can use L'Hopital's rule for limits at infinity or at -infinity, as well as limits that actually go to particular, where x goes to a particular number. You can also use it for limits where x goes to, infinity or -infinity, is all that it's saying. So, not necessarily something that you need to be writing down. We can try that on this one. So as a preface to this, we have a little graph here. Not a graph of this actual thing itself, but just to get a sort of intuition for what will happen. Here's x, here's y, and here's 2 curves. Here is the curve and I'll call this g of x, but it's basically just y equals x, right? It's a sort of 45 degree, even though that's not 45 degrees. It's a sort of 45 degree line that just sort of, y is whatever x is. On the other hand, here in orange, I'm going to have and the actual numbers don't really matter. Here's a function I'm going to call f of x, and it's the natural log of x. So note that as x goes to the right, towards infinity, both of these functions go to infinity. But one of them goes much faster than the other. Comparatively, the function x grows pretty steadily, like it sort of grows at the same rate the whole way through. Whereas the natural log of x starts off growing really fast, but then sort of, it's still going to infinity, but it starts going there really slowly. So it's growing, but it's not growing nearly as fast. Neither of these are the graph of this actual quotient, but maybe get a sense of why we're going to get the answer that we're going to get. Okay, so first, try direct substitution and confirm that you get an indeterminate form that you can use L'Hopital's rule on. And again, this isn't, you can't actually plug in 0, but it's as good as anything. Or you can't actually plug in infinity, but it's as, any mathematical way of sort of getting around this notation of looking like you're plugging in 0 is it's just going to be like, it's basically just going to be sort of like doing the same thing, but with the ability to say, well, technically I'm not plugging in 0, I'm plugging in something that's approaching, or technically I'm not plugging in infinity, I'm plugging in something that's approaching infinity, which, I mean, even if you do this the mathematically correct way, it's just going to be doing the same thing anyways. So, yeah. Anyways, the natural log of infinity is infinity, right? The natural log function is always growing, so that when you plug in infinity, it just is infinity. Okay, so we do get this indeterminate form. Okay, which means that we can use L'Hopital's rule. Which means that instead of the natural log of x over x, we'll be finding the limit of the derivative of the natural log of x over the derivative of x. Which is just going to be the derivative of the natural log of x is 1 over x. Right, so that's 1 over x on top of this fraction. And the bottom of this fraction is just going to be 1. So really it's just 1 over x is what it is. And if you plug in 1 over x, or if you try plugging infinity into 1 over x, you're going to get 1 over infinity. Maybe there should be an arrow instead of a... Okay, which is just 0. So the limit is 0. And part of the reason why this limit is 0 is, if you sort of take a look at this quotient and take a look at what the numerator and denominator are doing, that x that's on the denominator is growing much faster, when you're, going off to infinity. It's that denominator is growing much faster than the numerator is, so, the denominator sort of dominates the whole sort of thing, and it just sort of causes this quotient to shrink as you go off towards infinity, because the denominator is growing so much faster than the numerator is. Yes.
Is there ever a case where the derivative is going to give you an indeterminate too?
Yes, but in that case, you would just use L'Hopital's rule a second time.
Oh, so you get the second derivative?
Yeah. Whenever you get an indeterminate form, even if it's the result of having done L'Hopital's rule just previously, whenever you get an indeterminate form of 0 over 0, infinity over infinity, you can apply L'Hopital's rule, even if it's a second time around. Yeah. And we'll actually see one example of that. An example would be actually this back here. Right, so the limit of this is 0. if we sort of go back to this, we got 3 halves by canceling out the x's, but let's say we didn't. If we tried plugging infinity into there, we'd get another indeterminate form. Infinity over infinity, and you would take the derivative again. You would use L'Hopital's rule a second time and get 6 over 4. And that's 3 halves, so yeah. So you can use L'Hopital's rule as many times as you want, as long as you keep getting indeterminate forms of 0 over 0 or infinity over infinity. Where were we? Okay, we'll do one more example, and then we'll take a break before we sort of go on to the other kinds of indeterminate forms that we might see. All right, so another indeterminate form that you might get is 0 times infinity. So that is an indeterminate form, but it's one that you're going to have to change into being 0 over 0 or infinity over infinity. So these 4 limits that are right here, if you do direct substitution on any of these, you're going to get some combination of 0 times infinity or infinity times 0. So, for example, this first one, of course, the easiest thing to do would just be to cancel out these x's, and then you can sort of see, yeah, the limit is 1. Same thing here. You can sort of see that the limit is 2. But if you were to not cancel it out and try to just sort of plug, 0 into these, 1 over 0 would tend towards infinity, and, well, 0 is 0. And same sort of thing here, that you'd get infinity times 0 here. And for these last two, if you plug an infinity into this one, you get 0. Whereas if you plug it into x, that'll be 0 times infinity. And same sort of thing here. Okay. So, those are not the forms you want. They are indeterminate forms, but they're not the indeterminate forms you want. What would be better is if you had, aside from actually just canceling these out completely, what would be better is if you had something like this, because then you would get 0 over 0. Or if you had 2x over x, and you try to plug in 0, that would give you 0 over 0. Or if you had the limit as x goes to infinity of x over e to the x, that would give you infinity over infinity, which is the sort of form that you want. And the same thing would happen here if you had e to the x over x. You get infinity over infinity, which, these are better indeterminate forms to be getting because you can use L'Hopital's rule with these. So if you get the indeterminate form 0 times infinity, you're going to want to rewrite it in some way so that, usually it just involves like combining them into one sort of fraction, as opposed to having like, as a product of two things. But you want to combine them in some way so that you get these 0 over 0 or infinity over infinity forms. Yeah, so you might get other indeterminate forms, but you want to convert them some clever ways to 0 over 0 or infinity over infinity, because those are the only forms that L'Hopital's rule will work with. So if you had this limit here, and you sort of tried plugging it in as it was, another way of saying this would be the limit as x goes to infinity of 1 over e to the x times the square root of x. If you tried plugging in infinity into this as it is, plugging infinity into the bottom here, well, e to the power of infinity will surely be very large, and 1 divided by something that's very large, that's going to tend towards 0. And the square root of infinity is still infinity, so that's 0 times infinity. So you want to maybe smush these together in a way where you don't get 0 times infinity, but instead you get 0 over 0 or infinity times infinity. And the easiest way to do that is instead to write this as the square root of x over e to the x. Because if you directly substitute into this form, this way of writing it, you do get infinity over infinity. If you frame it in this way, you do get infinity over infinity, which is what you want. And this is the sort of framing or the way of writing it that you'll be using L'Hopital's rule on. So using L'Hopital's rule, this would become the limit as x goes to infinity of the derivative of the square root of x over the derivative of e to the x. Now the derivative of square root of x, maybe you've done it enough times to notice a pattern, maybe you haven't, but it is, the derivative of the square root of x is 1 over 2 square roots of x. Okay, and the reason that is because take the derivative of the square root of x. That's the derivative of x to the 1/2. And using the power rule, that's going to be 1/2 times x to the negative 1/2. You throw the power in front, subtract 1 from the power. You can send that x to the bottom as x to the positive 1/2, but like on the bottom, and that's 1 over 2 square roots of x. Right, so that's the derivative of the top there. And so that's going to be part of a complex fraction. And the derivative of e to the x is actually just e to the x. Okay. So now if you try direct substitution, on this sort of a, considering this to be the top and this to be the bottom, plugging in infinity, here, we'll actually do this. 1 over 2 square roots of infinity all over e to the power of infinity. It's going to be 0 over infinity, which is just 0. 0 over infinity is not an indeterminate form, it just is 0. Yeah. And actually, you can sort of see why this would happen if you sort of look at the graphs of both the square root of x and e to the x. So the square root of x goes like this. You guys know. It's just the sort of parabola that sprouts out from the origin and heads off towards the right. Whereas e to the x, the one that's on the bottom there, is this sort of exponential function that sort of, it grows faster and faster the further, more you go that way, it grows, like by the time that you get out all that way, it's growing like, it's almost vertical how fast it's going up. So that e to the x that's on the bottom is growing much faster than the square root of x that's there on the top, and so same sort of thing happens where the growth of the bottom sort of overshadows the growth of the top, and the whole thing just sort of shrinks down to 0 as you go off towards infinity. Not that that's sort of required for understanding this, but All right. Yeah. So that's limit's just 0 of this. Okay. Okay, so before we talk about the last kind of indeterminate form that you might, be having, that's going to require slightly different technique. Not really different, but just like it requires an extra step at the beginning. We'll take a break, and that is 0, right? Yeah. We'll take a break, and we'll come back at like 1:05. Yeah. To the infinity to the 0th power, 0 to the 0th power. I don't really know why that last one's there. Maybe there was a negative sign that was supposed to be in front of it or something. But just one thing I want to know is that this does not include 0 to the power of infinity, which just equals 0. I mean, if you have something that's going towards infinity, if you have something that's going towards 0, multiplying a bunch of them together, it's probably just going to take you to 0. Is why this is the way it is. But these 3 forms are indeterminate. But just the same as the others, you have to sort of, they're indeterminate forms, but they're not indeterminate forms that you can use L'Hopital's rule on directly. So you gotta do a little something to get it into a form to where you can use L'Hopital's rule. And these indeterminate forms arise when you have variable bases to variable powers. So something like, the simplest one, right, is something like x to the power of x. So, for example, the limit as x goes to 0 of x to the power of x, that would go to one of these indeterminate forms. And so, whenever you have a variable based on a variable power, that's when this happens. And I forget if logarithmic differentiation was a part of Cal 1. I think if you learned it, you would have learned it almost around the same time as implicit differentiation. Maybe like right after implicit differentiation. We're not actually going to be doing logarithmic differentiation, but we're going to sort of be taking a couple of cues from it. We're going to we're going to notice that we have this variable base to a variable power, and we're going to pull out the natural log function. Let's deal with these. So for example, let's say we have a limit like this. Okay. Now if you directly substitute, this, you'll get 1 plus 1 over, functionally what is 1 plus 1 over infinity to the infinitieth power. This is 1 plus 0 to the infinitieth, which is 1 to the infinitieth power, which is an indeterminate form, but not one that you can use L'Hopital's rule on. So in order to be able to use L'Hopital's rule, what we're going to do is we're going to sort of arbitrarily assign this limit a value of y. We're going to say that y is what this limit is. And we're going to assume that this limit exists and that it, that we can call it y. What we're then going to do is we're going to take the natural log of both sides. And the reason we take the natural log, and technically any logarithm would work, it's just that the natural log is sort of the one that we default to. Natural log of the left equals the natural log of the right. Oh, crap. I've once again forgotten the limit statement. Okay. Alright, so the natural log of the left equals the natural log of the right. We're just going to take advantage of a property of limits and the natural logarithm to sort of interchange the position of these two. So the natural log of y, natural log of whatever the limit value is the limit as x goes to infinity of the natural log of this thing. And the reason that we do this, this sort of natural log taking, is to take advantage of some of the log rules, really just the one particular log rule. That sort of allows us to take any power that's on the inside of a logarithm and just sort of toss it out in front of the logarithm. So that this is the limit as x goes to infinity of x times the natural log of 1 plus 1 over x. No, it's not all better, because if you try to direct substitute at this point, you'll get infinity times, well, that'll be the natural log of 1, which is 0. So it's still infinity times 0, but that's at least that's a little more manageable. Now what I'm going to do from here is so at this point I'll note that direct substitution gives infinity times 0. So what I'll do at this point is sort of try to shift it into being a quotient so that it can be 0 over 0 or infinity over infinity. The best way to do that is to say, okay, this is the limit as x goes to infinity of I put the natural log of 1 plus 1 over x on the top, and instead of multiplying by x, I'm going to divide by its reciprocal. Divide by 1 over x. That's the same as multiplying by x. Sort of the same as how, instead of multiplying by 2, you could divide by 1/2, and it's the same thing. Division is just, if division is just multiplication by the reciprocal, and it works the same in reverse. Multiplication is just division by the reciprocal. Okay. But now that we've sort of rewritten it in this way, if we directly substitute infinity into here, you've got the natural log of 1 on top, which is 0, and 1 over infinity on the bottom, which is 0. So 0 over 0, which means that it's all ready for L'Hopital's rule. Okay, so I'm going to steal this last line here. And that's where we'll continue. So natural log of y is this thing that does result in an indeterminate form 0 over 0. So use L'Hopital's rule. So the natural log of y should equal the limit as x approaches infinity of the derivative of the top of that over the derivative of the bottom of that. So the derivative of the natural log of this over the derivative of 1 over x. One thing I'd like to note is that the derivative of 1 over x, if you rewrite that as the derivative of x to the negative 1, you can use the power rule on it. Throw that negative 1 to the front, decrease the power by 1, and you'll have negative 1 over x squared. So negative 1 over x squared is the derivative of 1 over x. And that's just from the power rule, and we'll use that. Okay. So taking the derivative of the top, that natural log, it looks messy, but it's not so horrible, especially because something happens. The derivative of a natural log of something is just going to be 1 over that thing, maybe times something else, because chain rule and stuff. But we just take 1 and place whatever is in the natural log underneath. So 1 over 1 plus 1 over x. And because of the chain rule, we got to multiply, this is a composite function that we have on the top here. We got to multiply by the derivative of the inside as well. The derivative of 1 is nothing, but the derivative of 1 over x is negative 1 over x squared. Times negative 1 over x squared due to the chain rule. So that's the top of this fraction. And so yeah, we do appear to sort of have this sort of fraction inside of a fraction inside of a fraction. But it'll get better, because the derivative of the bottom, well, the bottom is just 1 over x, so the derivative of that is, again, negative 1 over x squared. And you can actually just cancel that out. To get that, this is the limit as x goes to infinity. The natural log of y is the limit as x goes to infinity of 1 over 1 plus 1 over x. And if you directly substitute at this point, throw infinity into here, 1 over infinity is nothing, and you'll be left with 1 over 1. So this equals 1. But 1 is not the limit itself. In the very beginning, we took the natural log of what the limit was, right? Y is our limit, and it's the natural log of y. It's the natural log of y that is 1. If the natural log of y is 1, it follows that y, which is what we sort of assign to our limit, is e. So the limit itself, like the value of the original limit itself, is e. Right, this limit from the very beginning, 1 plus 1 over x all to the x power, the limit of that as x goes to infinity, which is what we called y. That limit is e. Which is, like 2.718 something or other. But actually, this is one of the definitions of e. The number e didn't just pop out of nowhere. This is probably one of the first definitions of that number, like how to get that number that that was ever sort of developed. It was probably developed as a response to something like this formula being used for interest rates. You compound some amount of interest multiple times, which means you're compounding 1 over that amount every time. But anyways, that limit is e, and this is one of the definitions of that number. There are several more by now, but this is one of them. Okay, so if you get one of these exponential forms where you got 0 to the power of 0 or 1 to the power of infinity, just assign it a letter like y, take the natural log of both sides, then use that log rule to sort of pull that power, that variable power, away, into the front, so that you can rewrite it into something that you can use L'Hopital's rule for. And the last one we'll do, we'll skip example 7. You can also use this for one-sided limits. It works pretty much the same way. Okay. And this is actually one that we're going to have to do L'Hopital's rule multiple times for. Okay. So again, we have this sort of variable-based or variable power business, where if you directly substitute, sine of 0 is 0, so you'll get 0 to the power of 0, which is an indeterminate form, but not the one you want. So we'll call this y, and we'll take the natural log of both sides, just to be able to get that power down from the exponent. I mean, you can skip right to this part if you'd like. You don't actually have to write it this way and then go through the process of interchanging it. You can just write the limit first and write the natural log on the inside. But we'll use that log rule to sort of take that power out, put it in the front, and sort of just do the same deal as the previous one. Oops, no, it's the limit as x approaches 0 from the positive side of x times the natural log of sine of x. And at this stage, directly substituting in would give, well, you plug in 0 into here, that gives 0. Now, if you plug in 0 into sine, that's 0, and the natural log of 0 is actually negative infinity. You can sort of tell that if you look at a graph of the natural log of x. As x approaches 0 from the positive side, this sort of goes down towards, well, sort of just goes down forever. So that's 0 times negative infinity, which is, again, an indeterminate form, not one that we want, but maybe one that is, one that can be manipulated to be 0 over 0 or infinity over infinity. And in fact, we sort of, again, do the same thing as before. Keep the natural log on top. That's just the easier way to do this. And instead of multiplying by x, we'll divide by its reciprocal, 1 over x. This way, if we directly substitute, the top will, well, it'll be the same negative infinity as before, but the bottom, 1 divided by something that's approaching 0, is going to approach infinity. And so that is, that written like that, that is good to go for L'Hopital's rule. So using L'Hopital's rule, this sort of means we'll be taking the derivative of the top and of the bottom. Taking the derivative of the natural log of the sine of x. So take the derivative of this composite function on the top and the derivative of 1 over x on the bottom. Now the derivative of the natural log of sine would be 1 over sine, right? Just 1 over whatever's in the natural log, times the derivative of the inside from the chain rule. The derivative of that inside, of that sine of x, is cosine. And so we'll multiply by cosine. That's going to be our top of the old fraction there. And the derivative of 1 over x is, again, negative 1 over x squared. So right now, this is where we're at. Natural log of... What's up?
Can you, like, turn the top into cotangent x?
Yes, yeah, that is what we'll be doing. Yeah. Because cotangent is defined as being cosine over sine. And of course, every time I've done this, this is something that you can skip. You don't actually have to explicitly write that you're taking the derivative of the top and the bottom. You can just do it. This sort of step where we're at the ddx. So this is the limit as x goes to 0 from the positive side of this right here. Cosine over sine is cotangent. Actually, I'm just going to continue using this page. Okay. Now I'm going to do something here. I'm going to flip the numerator to the denominator and the denominator to the numerator. Okay, so cotangent is the reciprocal of tangent. Cotangent is cosine over sine, tangent is sine over cosine. They're reciprocals of each other. So if I have a cotangent on the top, that is equivalent to having a tangent on the bottom, because they're reciprocals of one another. Similarly, the reciprocal of negative 1 over x squared is negative x squared. If I just sort of flip that upside down, so instead of dividing by negative 1 over x squared, why not just multiply by negative x squared over 1, or negative x squared? So each side just, goes to the opposite side as its reciprocal. Now, direct substitution here at this point is going to give 0, and the tangent of 0 is also 0. So actually, we use L'Hopital's rule a second time. And I'm just going to skip the part where I say, d over dx or whatever. The derivative of negative x squared is minus 2x, and the derivative of tangent is secant squared. Let me just shove everything over to the left a little bit. You can rewrite this as negative 2x cosine squared of x. Secant is the reciprocal of cosine, so secant squared on the bottom means a cosine squared on the top. And finally, when you directly substitute this, 2 times 0 times 1. So this equals 0, which means the natural log of y equals 0, so that y must be 1. And that's what your original limit is, which you can kind of tell if you were to throw this into a graphing calculator. sort of see as it approaches x equals 0 from the right-hand side, it appears to be sort of approaching a value of 1. So this, is just sort of corroborated by the graph.